Hello students, in this session we are going to study the torsional equation. So, torsional equation for circular shafts. This is very important equation to solve any type of torsional type of questions, right? So suppose we have a circular shaft. Let us have a circular shaft like this. This is our circular shaft. And a torque is applied. A torque is applied to shaft. And we have already seen that there is some stress, shear stress developed when we apply a torque to this shaft. So what will happen? I am showing the another view, left side of view of this circular shaft. It is a circle basically, right? It is a circle like this, right? So this is a circle, right? So, and what is happening by applying the torque? Suppose the initial condition was this, and finally it came to this condition, right? There is some twist in this shaft, and if we see in the length, what is happening in the length? What is happening in the length? So this was the initial condition. Suppose this was the initial condition. This. And after twisting, there is a shear strain developed in this shaft, right? You know that the change in angle is the shear strain, right? We have already studied about the shear strain, and this is the angle of twist, and this is changing from A to suppose B, right? And when I will make here, it will be more clear. Suppose this is our initial condition, and then there is a twist taking place like this due to this torque, due to application of the torque, right? So this is a angle of twist, theta, from position A, this is our A position, this position, to position B due to this twist, right? And this is our center O. So this is happening that there is a twist, angle of twist, and this phi is the shear strain developed any length L, right? So we have already studied that when there is a shearing is there, there is a shear strain developed, which is given by tan phi, and because tan phi is nearly equal to phi for small angles, so we can write phi instead of tan phi, right? So what is happening here? And we want to find out the shear equation or torsion equation, right? So how we will interpret it, right? You can write right now that this shear strain phi, how we will find out phi? What is phi here? Let us remind that shear stress is proportional to shear strain within elastic limit. This we have read, right? Or tau will be equal to G phi, or phi can be equal to tau by G. This you should remember. This should be remembered. This is, we have already read in our previous classes when we were doing the shear strain and shear stress we were reading. Then we have done that shear strain is given by tau by G, right? And both have the same dimensions, so it has dimensionless. Shear strain is dimensionless. Now, what is shear strain? If we look at this, what is shear strain? So phi, here it is theta. So this is basically theta. This is basically theta. This is theta, right? So what is phi here? If I see here, this is phi is, remind that phi is given by the change in length. Here change in length is AB upon original length. This is given by L. Change in length upon original length. This is our shear strain, right? and we have already read that shear strain is given by tau by g. So this must be equal to tau by g, right? So one equation we have obtained. But what is AB? What is AB? AB is this arc, and suppose the radius of this shaft is suppose capital R, right? So then what is the length of this arc AB? That will be equal to r theta. This is, you know that the arc length is given by the radius multiplied by angle of twist. So angle of twist is theta and r is the radius. This is r theta. Put here, this is equation number 2. So put in equation 2, what you will get is r theta upon L multiplied by equal to tau by g. So you will get one equation, torsional equation, g theta upon L will be equal to tau by r. This is the one torsional equation, right? We will getting two torsional equations. This is one of that. This is equation number 3, suppose, right? Now in continuation, you should see that this theta is common for any radius. We have taken only outer radius here, but this theta is common to any radius. Like suppose I take an intermediate radius here, like this. Better to draw any place like this here, because this is also a side view of this. So better to draw here that if I take another radius, this radius, suppose this is our initial condition, and after twist this is our final condition. So this theta angle is for this small radius theta, or you can take here theta will remain same, right? So there is no difference in theta. So theta will remain same whether we consider this small radius r or capital radius capital R, outer radius. For each radius there is same angle of twist, that is theta. So angle of twist is same for all type of radius, right? Theta. So theta is independent of r radius, because at all radius the theta is same. So theta is same for particular type of twist. For AB, theta is same, g is already constant, L is also constant. It means that this g theta by L is constant for a particular torque, constant for particular twist or torque. This is constant, right? It means that this shear stress which is developed, this we are saying now that this is outer radius, because we have taken outer radius. That's why I am writing it tau r. Tau r shows that this is the shear stress outer radius. It means that this ratio g theta by L, this ratio is constant for all tau and r. So it can be said that tau r by r at outer radius will be equal to shear stress at inner radius. So this will be constant, that will be equal to g theta upon L. So finally we got that this shear stress depends on the radius, and it is maximum at the outer radius. As the radius changes, you can see here, if g theta by L is constant, it means it depends upon the radius. As the radius increases, tau increases. So tau at a radius r will be equal to g theta by L multiplied by the outer radius, right? And this tau is basically maximum. This is basically tau max. So tau max will be maximum at outer radius, and it is varying linearly because tau is proportional to r basically, right? So we have seen that the shear stress tau is proportional to small r radius, because g theta L by is constant for a given angle of twist, right? So you can see here that tau is proportional to basically r, and it is a linear variation, and r we are taking from the center, and at the center shear stress will be 0, and outer radius shear stress will be maximum and it is varying linearly. So what type of curve you will obtain for shear stress? For if you see here shear stress, you will get, suppose at any cross section we want to see, you will get the variation like this variation. At center the shear stress is 0, at the outer periphery shear stress is maximum, and like this, right? One side it will be different shear stress, other side it will be a complementary shear stress, because we have two shear stresses, right? So complementary shear stress, that you will get this type of curve, right? This is the shear stress, variation of shear stress. This is different, I am showing here because it's like this, right? And shear stress will be 0 at the center, and it will be maximum tau max, which is equal to tau r, tau at a capital R radius. So our equation now is this equation, tau by r is equal to g theta upon L. So our main equation is tau by r equal to g theta upon L. This is our main equation, right? This is our main equation. I am saying this equation number A, right? A number equation, tau by r is equal to g theta upon L, right? So how we have done this? Let us summarize it. We have taken a shaft, we have given a torque T, there is a twist from A to B, angle of twist is theta, there is a twist angle theta, and we are considering the outer periphery only, right? We can consider intermediate periphery also, but we are taking for the time being outer periphery. And angle of twist is same in each point, at each point angle of twist is same, right? So shear strain is given by change in length AB to the original length L, right? AB by L. And what is AB? That is r theta, capital R multiplied by the angle of twist, r theta. We have put here r theta by L, and we know shear strain is given by tau by G, so this will be equal to tau by G. So tau we are using here because outer radius is there, that's why I am writing here tau r for outer radius, right? In general we can write tau, but for outer radius I am writing tau r. So G theta by L is equal to tau by r. This is the equation. Now here we have seen that for a given angle of twist, theta is same for any radius, right? Suppose we are considering this point, suppose A dash was the initial point, and after angle of twist it will become B dash. So there will be same angle of twist in even any radius, right, for a given torque. So you will find that G theta by L is a constant for particular twist, or the ratio of G theta and L will remain constant. And if this ratio is constant, then this ratio will also be constant. At any radius the shear stress will be tau. At outer radius shear stress will be tau r. So we have generalized it that shear stress will be equal to G theta L into r. So by this we can say that tau is proportional to r because this is constant. G theta by L is constant. So tau is proportional to r. It means shear stress is varying linearly from the center. So this we have made the linear variation, and it is maximum at the outer periphery, which is given by tau r, which is tau max, right? So this is the first equation of torsional equation. Now second equation of torsional equation, second torsional equation, and then we will combine these two equations, First A equation is there, this equation is there. Now let us find out the second torsional equation. For second torsional equation, what we can do is we can incorporate the torque in between. We want to find out torsional equation in terms of torque. So how we can incorporate it? We can find out the small force acting on an elemental ring, because if we are applying torque, it is distributed in the material, so it will be having a different effect on the different part of the material. So what we can do is we can take a small element and we can find out force on that element and that force multiplied by radius will give the torque. So this is our circular shaft. This is the circular shaft, and we can take a small elemental ring in between, and what are the forces acting on that ring, we can find out that. So what is the force acting on that ring? So this is our ring. Suppose we have taken this ring, small ring of thickness dr at a radius r. So at a radius r, we are taking a thin ring of thickness dr. And what is the force acting on this small ring, and what is the stress acting on this small ring, shear stress, due to that force? We want to find out that, right? So what will be the force acting on this element? You know that force is equal to stress multiplied by area. So this will be, small force on this ring will be equal to shear stress multiplied by area. And what will be the area? That is 2 pi r dr, right? So we are keeping dA as it is, right? So shear force acting on this part of the shaft will be equal to tau multiplied by dA, right? And what is torque? What is torque? So torque will be force multiplied by radius. So that will be equal to dF multiplied by r. So that will be equal to, because at this radius it is acting, so torque will be dF multiplied by r. So that will be equal to tau r dA. Tau r dA, right? And from equation A, we can write that tau will be equal to g theta upon L multiplied by r, because we know that shear stress is varying linearly. So g theta by L was constant, but it is equal to g theta by L multiplied by r. We can put here, put equation number this, whatever is equation, this equation, suppose that 6 was the, this is 7th equation. So put equation number 7 in 8. What you will get? You will get the torque will be equal to, small torque on this elemental ring will be equal to tau. Tau is g theta upon L multiplied by r square dA. This will be the torque. And finding the total torque acting on the whole circle will be equal to, this will be equal to integral of this, and g theta by L is constant, so take it out, and this is r square dA. And what is r square dA? What is r square dA? That is polar moment of inertia. It is the definition of polar moment of inertia basically. R square dA. We have already read in the previous lecture. So torque will be equal to g theta by L into J. Or you can write T by J equal to g theta upon L. G theta upon L, and g theta by L is equal to tau by r. So this is tau by r. So this is the torsional equation. T by J, tau by r, g theta upon L. It contains two equations basically. Two equations. That g theta by L is equal to tau by r and g theta by L is equal to T by J. Right? So this equation must be remembered. This is the torsional equation. Right? Basically, for remember purpose, we use tau by r first and then g theta upon L. So that doesn't matter. It is better to use like this so that it is easy to remember like this, right? T by J, tau by r, g theta upon L. T by J, tau by r, g theta upon L. This is how this equation is remembered, right? So this is the way of deriving the torsional equation.